All right, that's better. Okay, hi everyone. My name is James Taylor. I'm an architect at Salesforce.com, and I'm going to talk to you about a top-level Apache project called Phoenix and how it turns Apache HBase into a SQL database. I want to first thank all the sponsors, and I really appreciate being selected and given the opportunity to talk with you all today. So a little bit about myself first. I've been with Salesforce for about 6 years, part of the big data group. Prior to that, I was an engineer at BEA Systems, where I worked on a product called Liquid Data, which is a federated query system. And I also worked on a project called WebLogic Event Server. In particular, there's a event processing engine that's part of that I contributed to. A little bit about the history of Phoenix. I started that at Salesforce about 3 years ago, and we pretty quickly realized that it was going to be generally useful. So we open sourced it first on GitHub. That was about a year and a half back. And we pretty quickly partnered with Intel, and we worked together, and we're getting good traction in the market, so we moved it to Apache. That was about 5 months ago. We started out as an incubator project, partnered with Hortonworks in addition. And again, we're seeing very good traction, and happy to let you know that as of May, we've graduated as a top-level Apache project. We've got people from Salesforce, Hortonworks, Cloudera, Intel, and NG Data as part of our PMC, so we have pretty good industry coverage there. Okay, so as far as what I want to cover, I want to answer two main questions. I want to tell you what Phoenix is, and I want to talk about why it's so fast. And then I'm going to move on and talk a little bit about a new feature that we added in our last release, which helps HBase scale in an entirely new dimension. So that's kind of interesting. And I'll touch on our roadmap and leave a little time for questions. Okay, so first, what is this Apache Phoenix? So I'm going to list 4 main attributes that define what it is. The first one is that it turns HBase into a SQL database. So I'm just curious, who here has a project where they're actually using HBase today? Okay, good. So what Phoenix adds above and beyond what HBase is a query engine. So Phoenix has a parser, a compiler, an optimizer, and an execution engine. It also has a metadata repository. So Phoenix stores all of your metadata in a kind of a system-level HBase table that we manage for you. So we'll store your table definitions, your indexes, your constraints, sequences, views, things like that, and we'll manage that for you. But from your point of view, it's a JDBC driver, like any other JDBC driver. We implement all the standard interfaces in JDBC, as well as the optional metadata interfaces. And one important point to make here is that Phoenix is really only for HBase data. We're not trying to solve the general SQL over Hadoop market. We're really just targeting HBase, which is important because it gives us a lot of our performance. Okay, number 2. Phoenix is the fastest way to access your HBase data. We do a lot of very specific push down into HBase, which push down is a technique for taking a part of your query and pushing it all the way down into the server so it actually executes on the server where the data lives. So HBase provides a lot of hooks for us to be able to do that. So that's one reason. The other thing that Phoenix does is it doesn't rely on MapReduce at all. Instead, what it does is it takes your query and it compiles it into a series of native HBase scans. And then it executes and orchestrates those scans and combines the results and returns it back to you just as a regular JDBC result set. Okay, how fast is it? Okay, so this is a very simple query that picks 3 rows out of a table, say, of a little over 100 million. It's querying by PK, so key is the primary key. Phoenix will execute this in 4/100ths of a second, so 40 milliseconds. The Stinger, the latest version of Hive, takes 280 seconds to execute it over the same HBase data. So 7,000 times faster, right? That's not really the end of the story, though, because as your data size grows, Stinger that time will grow linearly with your data set. So if you have 1 billion rows, Stinger would take about 40 minutes to execute this query, whereas Phoenix is actually going to take the same 40 milliseconds constant time for primary key type queries. Okay, so number 3 attribute that defines Apache Phoenix is it's lightweight. So there's no additional servers that you have to set up. It's all Java. As far as installation goes, if you use the latest Hortonworks distribution, then it's already bundled with that, so you don't need to do any setup. Same thing for Amazon EMR. It's part of that framework as well. But otherwise, all you have to do is you have to copy the Phoenix jar into the HBase lib directory and all your region servers. So even without those, installation is very straightforward. So let me show you where Phoenix fits in. This is a standard kind of HBase cluster architecture with your client on the upper left-hand corner, your HMaster, your region servers, and then at the bottom, HDFS. So on the client side, Phoenix fits in on top of the HBase client. So it hides the HBase client from you, and it replaces it with the JDBC driver. Then on the server side, Phoenix co-resides with the region server. We take advantage of some hooks that HBase provides called custom filters and coprocessors, which I'll talk about in detail a little bit later. And so that's how it fits in. So the 4th reason of what defines Apache Phoenix is that it's integration friendly. So I feel like we've kind of been adopted already as part of the Apache ecosystem and the Hadoop ecosystem, which is great. We have very nice integration with Pig. We also have integration with Flume. We have stuff in the works for both Scoop and Hive. So we're really kind of part of that ecosystem. And we can even map to an HBase table that wasn't even created with Phoenix. There are some restrictions around that, but if you follow the data model that Phoenix uses, then you can map to an existing HBase table, which is pretty interesting. Okay, so review. 4 things that define Apache Phoenix. It turns HBase into a database, into a SQL database. It's the fastest way to access your HBase data. It's lightweight, and it's integration friendly. Okay, so the second thing I want to cover is why Phoenix is so fast. 4 main reasons here. So number 1 is HBase itself. Obviously, HBase is very fast, but I like to say it's dumb, but it's dumb on purpose because it's not trying to be a query engine. HBase is a byte store and has very low-level, simple interfaces. So number 2 is the Phoenix data model that we define. So Phoenix has support out of the box for composite primary key definition. So I'm curious, I asked you guys before, like, who's using HBase? So I would like to ask, for those of you who are using HBase, who puts more than one piece of information in the primary key of your tables? Okay, so interesting. So we find that that's a very common practice with HBase, is to put more than one piece of information in the row key. And so Phoenix supports that out of the box. The second thing that Phoenix does in its data model is it ensures that the binary serialized format matches the natural sort order of your data. And so the reason that's important is because it prevents you from having to reorder that data when you see a query that's ordered in a certain way. The third reason why Phoenix is so fast is the client-side parallelization that we do. So HBase out of the box, when you do a large scan, it moves serially, region by region by region. Whereas Phoenix, on the other hand, looks at the start and the end key of the query itself, and it chunks it up by PK, and then it issues scans in parallel across all of those boundaries, and then it combines the results together. Okay, and the fourth and probably most important is the push down, or the way we push logic from the client through to the server to actually execute it on the server. And again, the way we do that is through custom filters and coprocessors, and that's what I'm going to focus on next. So what I'd like to do is I'd like to just set the playing field level and give you an idea of how the data model in Phoenix maps to the data model in HBase. So as you probably know, HBase, the basic building block is an H table. And then a table can be composed of one or more column families. And then column qualifiers are associated with a column family. So a column family can have any number of column qualifiers. And then finally, there's your row data with your row key, and as you know, key values. So what HBase actually stores is the key value, which defines the row key, the column qualifier, and the value itself. So how does Phoenix map to this? Oh, one more dimension is the time dimension. So HBase stores multiple versions where you're if you have the same row key, then those versions overlay older time-stamped versions. So that's kind of the HBase data model. Now, how Phoenix maps to that, so that Phoenix table maps one-to-one with an HBase table. And then there's two types of columns. So one type of column is a key value column. Key value columns map to a column qualifier in the HBase world. So essentially, what you're doing is you're predefining the column qualifiers that can occur in your HBase table. That's not to say that you can't define your schema at read time, too. So we do provide a feature called dynamic columns, which lets you specify the names of your column qualifiers at query time as well. Okay, the other type of column is your row key column. And these are the columns that make up your primary key constraint. And I'll show you an example of how that's defined. So let's say you've got a server metrics table, and it has a composite row key of the host plus the date of when that metric was collected. And then you have key value columns that represent the actual value of these particular metrics. So maybe you're measuring things like I/O time and response time and GC time and things like that. So this is what the DDL would look like to define that particular table. So this is just standard SQL. You've got your host and your date, and you've got your columns and your data types, and then at the bottom you've got your primary key constraint, which is declared as a composite primary key. So here's an example with data. So our dates are represented as an 8-bit long, 8-byte long, and then the host is just a string. So those are concatenated together, and those form the row key for your data, whereas the actual values live in the value of the key values. So now what I want to do is I want to walk you through an example using that schema that we just went over, where you're querying your server metrics table, and you're looking at, say, the last 7 days worth of data. And let's say you're only interested in hosts that reside in San Francisco, so you're adding a like clause for that. And then finally, you want to group by host and calculate an average response time. So this is a pretty basic query. So now what I want to do is I want to walk through 4 scenarios of the kind of push down that Phoenix does to make these queries run so fast. So there's 4 areas I'm going to cover. Our skip scan filter, how we do aggregation, TopEnd queries, and then I'll conclude with how we do hash joins. Okay, so first the skip scan. So the skip scan filter kicks in when a query uses your columns from your primary key constraint, which is the case here. So we've got both date and host make up your primary key constraint. So the query engine in Phoenix will know that it can use the skip scan. Okay, and so let's say your table has 4 regions worth of data. So the first thing that Phoenix will do is it will parallelize the scans, like I mentioned before. So in this scenario, let's say we're taking that one query and we're going to issue 3 parallel scans. So what will happen is we will push through the range information from your query for the date column and for the host column, and we'll use our custom skip scan filter to skip through your key set for each region. So you'll basically skip, say, 83 days worth, assuming you have 90 days, and only look at the last 7 days worth of data. And then you'll again run out of that, and then you'll again skip 83 days worth of data for the next host, and include and skip and include and skip. So essentially what you've done is you've skipped 90% of your data. Okay, so aggregation. So how do we handle the group by part of this? Well, for that, we have a group by coprocessor that gets invoked, and it gets pushed the expressions that you're grouping by. So that forms a kind of key for your groups. And then what Phoenix will do is it will run that scan on the server side, and it'll keep track of all the distinct groups that it sees. It'll aggregate on the server side, and then what it'll return from that coprocessor is a different scan that only includes the distinct group by keys that it found. So in this case, it took all your raw data and only returns 3 rows back with the aggregated information. So it's a really good way of conserving your network bandwidth, essentially. It would work equally well if Phoenix returned all the data to the client and we did the aggregation on the client. It just wouldn't be as efficient. Okay, so what about the same query, but instead of an aggregate query, it's a TopEnd query. So a TopEnd query is typically where you define an order by and a limit together. And so essentially what you want to find here is the top 5 GC times across your last week's worth of data. So that same client-side parallelization that I already talked about will happen. The skip scan filter will also occur just like before. But the rows that pass through that skip scan filter will then go into our TopEnd coprocessor. And for each scan, what we'll do is we'll hang on to the 5 rows with the biggest GC time. And then for those 5 rows across each scan, we'll do a final merge sort on the client side and return to you the 5 rows with the top GC time. So this is much more efficient than what many systems would do, which is sort your entire data set and then return the 5 biggest GC times. So this is going to outperform that by quite a bit. Okay, I'm not going to go into too much detail on secondary indexing, but I did just want to mention it because basically I want to give you an idea of what's happening behind the scenes when you do add a secondary index. So in this example, let's say you've executed that TopEnd query and it's still not fast enough. So if you add this index, then you'll basically have Phoenix will create for you a table that represents your secondary index. And it'll have a different row key structure. Essentially, it has a row key structure defined by the columns that you're indexing. And then any additional columns that you include will be key values in that table. And then what Phoenix will do is at compile time, it'll notice that you have an index, and it will choose the query plan that is most efficient. So in this case, your query wouldn't change at all, but behind the scenes, Phoenix would rewrite the query to actually query the index table instead of the data table. One thing to note is we don't have stats yet. We're working on that, but we basically take a conservative approach, and if your data is not part, if your columns that you're referencing aren't part of the index, then we won't use that index. So we won't try to join back from the index table to the data table because we don't know how selective the index is right now. But since we know that all the data is in the index table, we know that a query over that index table will be more efficient in this case than a query over the data table. Okay, now the last case of pushdown I want to talk about is the hash join. So this is an example of a query where maybe you're joining your server metrics table with some auxiliary table that may have additional information about your host, for example. So here's the join key. And so essentially what Phoenix does is it teases apart each part of the join and isolates the parts of the query that run over each table. So in this case, you've got your server metrics table and the where clause, the filter on that where clause, and the order by and the limit all apply to that table. Whereas the other side of the join, the location information, this is what applies for that. So we tease those two apart and we end up with two queries now instead of one. So what we'll do is we'll take that left-hand side and we'll execute it completely on the client side, and we'll take the results of those rows and we'll compress them and broadcast them once to each region server. The region server will hold on to that, and then the client will run the left-hand side query, and our join coprocessor will use an in-memory map to join the right-hand side with the left-hand side as the left-hand side scan is running, and then we'll return the joined rows back to you. So that's how the pushdown for hash join works. Okay, so next I want to just shift gears and I want to talk a little bit about how Phoenix can actually help HBase Scale. So we introduced a new feature in our last release that allows you to define a view, regular SQL view. And essentially what the view does is it defines, so all views over a given table, views are not materialized. So a view is essentially a view onto a single physical HBase table. And then on top of that, we built support for multi-tenancy, and I'll show you an example of that in a second. So how does this help HBase Scale? Well, it turns out that HBase really prefers a small number of really big tables to a large number of small tables. And the reason is HBase consumes resources for every region, for every column family, for every table. And if you have too many tables, you'll run out of resources pretty quickly. So here's an example of a view. So the base table looks like any other table. It's in this scenario, it's an event table that we're defining. And let's say you define an event type and you define an event ID as a primary key. Now at the bottom, I'm showing you how you define a view on that. So again, this is standard SQL syntax. So you create a view and you specify a where clause. And that where clause identifies a type equal to W. So maybe you've segmented your events by type. So here's what it looks like. You have a single Phoenix event table and a single physical HBase table called event. And then this will be segmented based on your views. So maybe you've defined 4 views with a where clause with the type that I've shown here for each one. So big deal, you may say, is instead of 1 HBase table, or sorry, instead of 4 HBase table, I only have 1 HBase table. But the time when it becomes interesting, and this is what I'm going to talk about next, is for multi-tenancy. So given the same scenario, let's say I want to make that event table multi-tenant. So the way you do that in Phoenix is you define a column that identifies your tenant. And that it needs to be the first primary key column. It doesn't matter what it's called, but it needs to identify your tenant in your data. And then you add that as part of your primary key constraint, and you declare a table to be multi-tenant by tacking on that multi-tenant equals true property. So given that, now when you specify a connection, if you want to specify it as a tenant, then in your connection string, you define which tenant you're connecting as. And so this tenant ID in this case is me. And then through that connection, when you create a view, so you're actually creating a view for that particular tenant. And so this is what the table now looks like, segmented by tenant ID. So I don't know about your organization, but Salesforce, there'll be over 100,000 potential tenant IDs. So there's no way that you could have a separate physical HBase table for 100,000 tenants. It just wouldn't work. So instead, we've modeled this through views. So now here's zooming in on one of those segments of a tenant. You'll have a further subdivision along the type axis. So that gives you an idea of how one event table will be subdivided by both tenant and the event type. Okay, so there are some restrictions in terms of what you can and can't do in the DDL. One is that the primary key constraint of your base table can't be changed by a view. We are entertaining allowing you to append to it, so that's kind of interesting, but you can't change the base part of what's already there. Another interesting thing is when you connect as a tenant, you only see your own data, and that includes the metadata APIs as well. So it's kind of interesting. You can connect as a tenant, and you'll see your tables as you've defined them, and on top of that, you can create additional columns that are only for your view, which is nice, which is very different than what the relational world allows you to do. There are also restrictions on altering a base table. So currently, once a base table has views associated with it, we don't allow you to change that primary key. That's likely something we'll relax in the future. And we don't allow you to drop columns that you've referenced as part of your where clause in your views. So that gives you an idea of multi-tenants, multi-tenant tables, views, and how we help HBase scale in this new dimension. So finally, I just want to talk a little bit about our roadmap. So a couple items on here have already been implemented. Derived or nested tables, that's where you do a select and then you issue another select in the from clause. So that's already implemented. Local indexes is an interesting one. This is something that some folks at Huawei have contributed to Phoenix, and it's an alternate kind of complementary indexing strategy. Our current indexing strategy creates a global table, whereas this creates, basically it co-locates the index rows with the data rows. And this has certain advantages. Certainly at write time, this speeds up writes, because when you write, all the data is local for the index updates. It also helps with the join case. So in this case, you can have an index that's not covered, and it will join back to the data table because we know that the join will simply be a local get on that region server, so it's not a very expensive operation.
I have one question.
Yeah, hold it to the end if you don't mind. A couple other things. Transactions is something that we're working on. There's quite a number of already implemented transaction modules on top of HBase, so we're evaluating those, and we're going to figure out which one works best for Phoenix, and we're going to integrate with that. We're going to introduce some more join strategies, namely handling the kind of many-to-many joins that don't really work for a hash join scenario. We're also going to implement correlated subqueries. And as I mentioned before, we're going to start down this cost-based query optimizer path, namely collecting stats for tables and driving optimizer decisions based on the stats that we find. And then finally, we would like to implement the OLAP extensions that SQL provides, which is namely the windowing and partition by and ranking and those types of things. So that gives you an idea of our roadmap. So that's pretty much it. I just want to open it up to questions now for people who have questions. Thank you very much.
First, what kind of integration do you offer? Do you offer any ODBC drivers, JDBC access, etc.? That's the first question. And the second, any integration with HCatalog, Hive MetaStore?
Okay, good question. So two-part question. Do we provide an ODBC driver? No, we don't provide an ODBC driver, and we would love to partner with someone out there who wants to help us with that. I hear Facebook maybe has an ODBC driver that they have for Presto that might be a good fit. Postgres has one as well. That might be an interesting option. Currently, we only have a JDBC driver. Another option might be implementing a simple kind of thrift-based ODBC driver, kind of along the lines of what Hive does. The second part of your question was, let me think, I'm blanking. What was the? HCatalog. HCatalog, oh, HCatalog. So we would love to integrate with HCatalog, but the issue there is that you can't define everything that we need to in it. So namely, we need to be able to define composite primary keys, and we need to be able to define null and not null constraints and things like that. So if HCatalog comes a little farther and we can define those things, we would love to integrate with that. That would be a very good idea. Yeah?
A couple of questions.
Sure.
Where are all of these definitions come from the views that were defined?
Okay.
And the second question is there more granular control like read-only access than retry?
Sure. So all of the metadata is stored in an HBase table kind of behind the scenes in this table called system.catalog. So it's really just another HBase table that Phoenix manages for you. So when you issue, for example, an alter table statement, then we actually will update that table for you behind the scenes. And the second part, did you have a second part to your question?
Yeah, managing access like read-only.
Oh, read-only access. So yes, so views are not always updatable. It depends on what your where clause looks like. So we only support updatable views if the where clause is simple column equal something kind of constraints separated by ands. So that'll be an updatable view. But if it's not that, then a view will be read-only. Also, if you create a view that's mapped directly to an HBase table, which we allow, then it'll always be read-only. We do have a JIRA, though, that would even like to be able to declare that a view is read-only in the case that it otherwise would be updatable. But that's not implemented yet. You had a question.
Actually, I have a different question. I figured out the first question, but
Okay.
What are your semantics in the face of timeouts? Like say TopEnd Query.
Right.
What happens in a TopEnd Query if one of the regions doesn't return it?
The query will fail. We don't try to, have some retry logic above and beyond the regular retry logic that HBase does with its scans. Do you mind? Can you run over to the mic? Do you mind? Or talk really loud?
Skipping set is there, right?
The skipping, yeah, skip scan.
You skip the data, right?
Right.
So can you please go to that slide?
Sure. That's the top end. Okay, this slide? Okay. Oop. I did it. Yeah, so the way it works, let me show you the query. So see how both the date and the host are used as part of that query? And by the way, if you're familiar with it, like the fuzzy row filter, which is a filter that ships with HBase, skipscan is kind of like that, but it's kind of like that on steroids. You know, but functionally, it's the same idea. So you see how host and date are part of your row key, right? They define your row key. And then on the right, you've got two constants. You've got the current date minus 7, which becomes a constant at compile time. And then you've got a filter of anything that starts with SF, which is another constant, but it's a range, right? It's SF to, you know, SG, non-inclusive, right? And so that range information is pushed through our skipscan filter. And then we have some code that essentially starts walking through your data and knows when something's in range or out of range. And if it's out of range, it knows where to skip to. That's the next based on navigating your key ranges, essentially.
Basically, hashing something does in order to skip the ranges. How it knows internally to skip certain ranges now? Because when we say the date is a constant, minus SF is not a constant, it's a string basically. So how it skips that means how it senses that value and how it moves to the next step or between that range.
Right. Well, take an example. So you want to match things that begin with SF, right? And then you know what date you want to start at, right? So you can seek right to the row that starts with SF plus a date range. And then as soon as you go past this SF part, then you know you need to skip again, right? So I don't know. It's hard to sit up here and explain. Look at the code. It's open source. Yeah.
What are the semantics of on delete of secondary indexes? So I delete a row, so there should be a delete of the secondary index pointing to that.
Right.
In the case of the global and so the local one seems nice. It's located on the region server. You can push down that right. Sufficient. What about the global case?
So the global one, yeah, there's a little more kind of plumbing behind the scenes, but basically we have a coprocessor on put. So when your delete occurs for your data table, then a coprocessor wakes up, and there's logic that we push so it knows how to take the row key in your data row and transcribe it to the row key of your index row, right? And then it may issue a cross-server call at that point to update or issue a delete for that particular index row.
And if that fails, then it doesn't delete the primary row.
If that fails, then the whole operation fails. And that's one of the trickiest things is like, how do you handle that types of failure, right? We have a failure policy you can declare, but by default what we do is we disable the index table, and then you have to rebuild it manually. Or we do these tricks where we write wall updates for both the data and the index row together in the wall. And then when the server comes back up in the event of a server crash, it'll replay the write edits for both the data table and the index table. Maybe one more question. I think we're out of time. Yeah?
So how Phoenix handle the concurrency? Say if we have many users use the Phoenix platform at the same time.
Right.
What's the performance look like?
So it's similar performance to what HBase has in that scenario, right? Everything in Phoenix is tunable, so you can say, given a query, how many parallel queries you want it to spin up, right? So if you want to balance that, you can lower that number, so we'll spin up less threads to process any one query, depending on your use case. But however basically HBase handles it, that's essentially how Phoenix is going to handle it as well. Because essentially, at the end of the day, it's issuing scans just like HBase is. Okay. Thank you. Thank you very much.